In this video, we're going to take a look at how we can use our percentage composition and mass percent to determine formulas of compounds that might be unknown to us. We might have some general ideas to what elements are in there, and we might have their mass percent and percentage composition. And from that, we can perhaps determine what the actual number of atoms are within that compound. We can figure out what those little subscripts are. So, for example, if we have CX, HY, OZ, and we have the mass percent and other information, we can figure out what X, Y, and Z are. There are many compounds that are made up of C, H, and O, but what makes them different is their mass percent, and as a result, the number of atoms of each type that make up that compound. So using our mass percent, percentage composition, and other information, we can actually figure out what the exact atomic ratio is and the number of atoms of each type of element within a compound. Before we begin, we need to actually understand two important definitions or two different types of formulas. We have something called an empirical formula and something called a molecular formula. The molecular formula, I sometimes call it the actual formula because that's what it is. It's the actual formula of a molecule. It tells you exactly how many atoms of each type there are in that molecule. So if I ask you for the molecular formula of hydrogen peroxide, you would tell me H2O2. There are two H's and two O's within that molecule. The empirical formula is something that I also call the simplest formula. It's the reduced formula. It's the lowest whole number ratio of the elements in that compound. So it does not accurately express the composition of the molecule. It doesn't really tell you how many H's or O's there are. It just tells you there are H's and O's and the ratio of that. So for example, here I have hydrogen peroxide. Its molecular formula is H2O2, telling me exactly there's two H's and two O's. But sometimes I might not have the exact formula. I might just have some information that'll get me what's called its empirical formula. Its simplest ratio. So you can see here 2-to-2 ratio is the same thing as a 1-to-1 ratio. Like when you reduce a formula, divide by 2 here. And so our empirical formula for hydrogen peroxide is HO. Over here we have another compound, H2F10. This is our molecular formula. But if I were to ask you for the empirical formula, you want to find the simplest whole number ratio. So divide by 2, divide by 2. And so our empirical formula would be HF5. And you might be asking, well, why do you want that? Well, the thing is, sometimes you don't have a choice. Sometimes you do a mass analysis and you can actually figure out for that compound its empirical formula. At least you have some general idea to the ratio of the atoms. Then you can use other information to eventually work your way to find the actual formula. So basically, the empirical formula is very, very useful because it's kind of the first step that you need in order to figure out, well, what your actual molecule is. So the interesting thing about empirical formulas is that many compounds can have the same empirical formula. So we'll do a couple examples together. Over here we have C6H6 and C2H2. These are two different compounds. These are the molecular formulas. We have C6H6. If I want to find its empirical formula, I reduce it, divide by 6, I get CH. For C2H2, same idea. I reduce it, I get CH. So you'll see that even though these compounds are different, one has 6 C's, the other one has 6 C's and 6 H's, the other has 2 C's and 2 H's, when you find their simplest whole number ratio of atoms, for the atoms, they have the same empirical formula. So a great example of that would be the C6H6 and C2H2. They do have different percent compositions as compounds, but when you're doing an analysis, initially you might just find the empirical formula, and so that doesn't quite tell you, which it is. That's why the empirical formula is not the actual formula. It's just the simplest ratio. Now at least it kind of it brings us to the point where we realize, okay, if it's a 1-to-1 ratio, if we find that our empirical formula is CH, at least we know it's going to be a 1-to-1 ratio. We know it's going to be either C6H6, C2H2, but we know it wouldn't, for example, be CH4 because that's not a 1-to-1 ratio. So at least that tells us what our compound is not if it's an unknown compound to begin with. We can do a few more examples together so you can find the empirical formula for the other compounds here. So C9H12O18. I just want to mention that you should not have decimals or fractions in your empirical formula, because by definition it's the simplest whole number ratio. That's super important. So if you divide by 9 over here, that probably wouldn't work out. Try dividing maybe by 3 and you can get C3H4O6. Try this one here for glucose on your own, and you will probably get CH2O. And then lastly, let's try H2O. Interesting. You'll notice that H2O, its molecular formula and its empirical formula are the same. It's already in its simplest whole number ratio. So many compounds have molecular formulas that are the same as their empirical formulas. So a great example of that would be water. So what we're going to see is how you can figure out an empirical formula from percentage composition. Again, you're using this because you have percentage composition, you have that data, you have mass percent of each element in the compound, and so you want to figure out, well, what the compound is. What is its actual formula? Your first step before you can get to the actual formula is finding that empirical formula. Once you have the empirical formula, then we can do some fancy math, not really that fancy, it's actually very logical math, to figure out what the molecular formula is. So here I've included the steps for how to find your empirical formula. You can refer back to these. We're going to take a look at the steps as we do a problem together. Make sure you have your calculator out, because you're going to try these problems along with me to make sure that I'm not making mistakes, and to make sure that you can also see how to get these same numbers in your calculator. So you want to train yourself to use that calculator effectively. Here you can see some other problems translating from molecular to empirical formula. So you should understand that it's the simplest whole number ratio. And again, you'll see that some compounds have the same molecular and the same, their molecular formula is the same as their empirical formula. And you'll also see that some compounds, different compounds, have the same empirical formula. We had seen this example earlier, but I just want to show you how different these compounds are. Here we have the molecular formula for C2H2 and the molecular formula for benzene, C6H6. Look at benzene, it's basically a carbon-hydrogen ring, whereas acetylene, C2H2, is a linear molecule. So they're very, very different, but when we first find their empirical formula, they have the same one, because they have the same ratio of carbon to hydrogen, a 1-to-1 ratio. So that's why it's important to eventually get enough data to convert that empirical formula to a molecular formula to figure out which one it actually is, because they do have very different properties. So to determine the empirical formula, there's a really cool rap that people come up with, or a little poem that people come up with. You can remember it this way. I'm not going to rap it out, but you can. Percent to mass, mass to mole, divide by small, multiply till whole. So if you remember that rhyme, that will help you to remember the steps that you need in order to figure out the empirical formula of a compound. Here we have a flow chart to help you remember the steps. So percent composition first, find the mass of each element. You assume 100 grams for that. You find the moles of each element by using your mole formula. Mole is equal to mass over molar mass. Then you find your mole ratio, and then you divide by the smallest mole number, and then you multiply until whole to get your empirical formula. And right now it might not make sense, but when we do the problem together, it will make a lot more sense, and you can come back to the flow chart to take a look. All right, so let's try this problem out here. Calculate the empirical formula of a compound that is 85.6% carbon and 14.4% hydrogen. So my first step is to write down a skeleton formula for the question, meaning I know my compound is made up of C and H. So I'm going to write this. I'm going to put CX, H, Y. My goal is to find X and Y At least I have some goal in mind. I know it's CH, now I need to find what X and Y is. Is it a 1-to-1 ratio? Is it 1-to-2? Is it 2-to-1? What way is it going to go? Typically in questions like this, you usually want to put C first, followed by the other elements. So usually it's C, then H, then O, N in that order. But you'll learn more about that later on. So our next step is to assume 100 grams of the compound. If you assume you have 100 grams of the compound, that means that these percentages can be seen as grams, as masses. So if I have 100 grams of the compound, that means that I have 14.4% of 100 grams is 14.4 grams of carbon, of hydrogen, 14.4 grams of hydrogen. And then likewise, I have 85.6 grams of carbon. So that's how we assume 100 grams. That's our next step here. Okay. So skeleton formula, and then assuming the 100 grams. So now I just want you to go to your periodic table to find the molar mass. So for carbon, the molar mass is 12.01. For hydrogen, 1.01. And put the units grams per mole. Your next step is going to be to convert the masses that you had from the previous, from your data up here, into moles by using your mole formula. Remember, the number of mole, can be found by doing your mass over your molar mass, big M. So for carbon, we had 85.6 grams divided by our molar mass, which is 12.01. Put that in your calculator just to see if you get the right answer. So it's 85.6 divided by 12.01, and we get 7.13 moles. So I'm going to write that down over here, 7.13 as the subscript for carbon. Now we can't have decimals, but don't worry, we'll fix that in a second. Our next step is to do the same thing for hydrogen. So we had 14.4 grams of hydrogen divided by its molar mass, 1.01. So let's do 14.4 divided by 1.01, and we get 14.3 moles. So let's put in 14.3 here. Now, our next step is going to be to divide the numbers that we found. So we had 7.13 for carbon and 14.3 for hydrogen. You're going to find the simplest whole number ratio by dividing by the smallest number of the two. So 7.13 is smaller than 14.3. So what we're going to do is 7.13. That's going to be what we're dividing by for both of them. Let me erase that. This should be a 7 here, 7.13. When you do that, so try it out in your calculator, one of them will be 1, so carbon will have a 1 there. I don't really have to put it, but when I'm doing my work, I do like to write down 1 just to remember I did this step. And then hydrogen will have some decimal places associated with it. So I'm just illustrating this here. I left a few more decimal places than I should have in terms of my significant figures, but just to illustrate a concept. Again, I can't have fractions, so I could actually round in this case. There are some rounding rules that we have to follow. If the decimal you end up with after dividing by the smallest is between 0.95 and 0.99, you can round up. So for example, if I got 7.95, I could round up to 8. If the decimals are between 0.01 and 0.05, or even smaller than that, okay, so let's say smaller than 0.01, so you have 0.00 something, 0.00000 something, you can round down. So for example, here I have 2.00 something. That's less than 0.01. So I can round down. I can safely round down to the nearest whole number, which would be 2 in this case. So I have C1H2. So according to my rounding rules, I can now round the 2 down, or I can round the 2.005 down to 2. My 1 I don't have to rewrite in there, and this is my empirical formula. It's my simplest whole number ratio. It doesn't mean that this is my molecular formula. Doesn't mean this is the actual formula. It just means that in this compound, I'm going to have a 1 to 2 ratio. It could be C2H4. It could be C3H6. We don't know, but at least we know what the ratio is going to be. Now back to the rounding rules. If I wasn't lucky enough and I didn't get the situation where I could round either up or down, I'd have to do an additional manipulation. I'd have to multiply until I could round. So here's an example. Let's say I ended up with C1.5H3O1. The 3 and the 1 are good, but the 1.5 I can't round up. I can't round down. It's not in these defined values here. Okay? So what we need to do is we need to multiply until whole, or until I can round. So for example, C1.5H3O1, if I multiply by 2, then the whole thing becomes C3H6O6. When I multiply by 2, I have to multiply every subscript in the compound by 2, not just one, every subscript. And those numbers are now 2 times larger. But you'll notice that my decimal I couldn't round before is now 3. So now I've solved for it, and I found my empirical formula. If you are not sure what to multiply by, there's a handy table to help you when you're doing your homework over here. So for example, if your decimal ends in 0.67, the recommendation is that you multiply by 3, all subscripts, and it should get you to a whole number that you can actually round up to, okay, or down to. So make sure you remember these rounding rules. They're super important. And we're going to try another problem where the rounding rules are going to be, where we're going to have to do some further manipulation because our numbers won't be super easy to round. So here we have another question. We have a fuel. We don't know what it is, but we know there's C and H in it. So we're going to write down our skeleton formula, CXHY. Same idea. We're going to assume 100 grams of the compound. And so the percentages become the masses. So we have 18.3 grams of H. And we have 81.7 grams of carbon. We can go find our molar masses in the periodic table. 12.01 grams of grams per mole for carbon and 1.01 for hydrogen. And we can go in and put our numbers and do our calculation to find our number of moles. Let's just make sure that's right. So we had 81.7 grams of carbon divided by 12.01, and it gives us 6.80. That's right. And then hydrogen, let's try that out. 18.3 divided by 1.01, and it gives us 18.1 moles. So we write that in here. We have 6.80. Now I recommend in your calculator you keep all your digits, because if you round too much, you're not going to get the right answer. So make sure that you keep all your digits until the very end. And then make sure your final answer is what matches with the sig figs. But in this case, it doesn't really matter too much. We care more about that final formula here. So now we're going to divide by the smallest, so 6.80 to get the simplest whole number ratio, 6.80. And we get C1 H2.66. Our 1 is fine, but the problem is our 2.66, we can't round it. It's not in these ranges here, or it's not smaller than this 0.01. So what we need to do is we need to multiply by something that will make this 2.66 whole, or at least close enough that we can round it. So let's go to our table. You'll notice you have x.67. They suggest multiplying everything by 3. So let's do that. Let's multiply that whole thing by 3 here. If we do that, I'm just going to put times 3 over here. The 1 becomes a 3. And do 2.66 times 3 in your calculator. You get 7.98 over here. Now, you can't leave it as a decimal number like this, so you can actually round, because it's now in between that 0.95 and 0.99 range. So we have C3 H 8. So this, not this here, this is our empirical formula. It's a 3:8 ratio. It doesn't mean it's our actual molecular formula, but we know it's going to be a 3:8 ratio at least, or a 3:8 ratio for sure. It could be maybe 6:16, but we don't know. We need further information. We just know what the empirical formula is. So that means that now we can round that 7.8 to 8. We don't have to put 8.0. You can just put C3H8, and that solves for your empirical formula. So again, here's the table of suggested values that you can try multiplying by in order to get these into rounding ranges. There's a few more practice problems you can attempt that'll come on the following slide here, a few slides here, so you can try them out with the solutions. Try them before you actually look at the solution. This is just a table again of suggestions. I know I had said 0.95 to 0.99 and 0.01 to 0.05. That's sometimes a bit too stringent. You don't really need that high of a value to round up or round down. So we'll actually stick with these values here. If it's 0.85 and higher, you can just round up. If it's 0.15 or less, you can just round down. Those are reasonable decimal places that you can round up and down from. They should work just fine, especially when we do labs. We might not get quite to that 0.99. We won't get to that purity level. We want to try to, but we're going to really try to round if it's 0.85 and higher or 0.15 or less. We can round down. Any other things, any other values that are not in those areas for rounding up and down, we need to do our multiply by to get the whole number result. Again, try these practice problems out and then verify your answers. Here are some more practice problems along with some readings to do in your textbook. So sometimes you're going to have more than two elements, and the same idea applies. Make your skeleton equation, except your skeleton skeleton formula will be CXHY, and then whatever other elements in there, OZ. You don't have to put Z, you could put A if you want to. You could put A, B, C, I don't really care. As long as I know you're looking for those subscripts, that's what really matters in this situation here. So, great, we found their empirical formula, but we want to know what the actual molecule is. We want to know what the actual compound is. We want to know what the exact atom number is in that compound. Is it HOH2O2? Is it H4O4, if that exists? What is it? So we need a bit more information. If you want to find your molecular formula, your actual formula, once you have your empirical formula, well, you need to know the molar mass of the actual compound that you're looking for, the molar mass of the molecular formula. And you might think, well, how can I find that? If I don't have the formula itself, how can I find the molar mass? Well, there's a little machine that chemists can use, not just chemists, really anybody who wants to find out a molar mass, called a mass spectrometer. And there's a picture of it below, and I'll show you how it works just briefly. I want you to get that science is not magic. There's actual equipment we have to build to figure this stuff out. It takes a lot of brain power to go into building this. So basically what you do is you take the sample of the unknown compound that you're looking at, and you ionize it. So basically you remove electrons from it. Electrons don't weigh much, so it won't really affect your result too much. So their mass is negligible. You shoot the sample, so your sample starts off in the source here. You shoot the sample through a magnet, and basically because the sample is ionized, has charges to it, the sample would be deflected. And so you can use a degree of deflection to figure out, well, what the molar mass of that compound is, what the mass of the compound that went through the magnet is. So if you have, if you don't have a lot of deflection, or if it's more, let's say on this end here, your mass is high. If there's more deflection, you have a lighter molecule overall. So you just shoot your ionized sample through the magnet. The degree of deflection gives you a general idea as to what the mass is. We might have thrown in some known samples with known masses, and then wherever your unknown sample lands, if it lands to a known one, let's say we knew what, a sample with 46 and your unknown lands at 46, then we know that your mass is also 46. So the general idea is that the degree of deflection of your sample tells you what the mass or molar mass of the substance is. So once you have the molar mass of the molecular formula, you can use the molar mass of the molecular formula to figure out what the molecular formula is from the empirical one. And so the general formula is A times empirical formula subscripts. A represents a multiplying factor. A multiplying factor. Multiplying factor. And so we're going to take a look at how to figure out that multiplying factor so you can get your molecular formula. Okay, so here we have a sample problem. The empirical formula of ribose, a sugar, CH2O, is CH2O. That's the empirical formula. It's not the actual formula. We just know there's a 1-to-1 ratio. 1 carbon for every 2 hydrogens for every 1 oxygen. In a separate experiment using a mass spectrometer, the molar mass of ribose was found. So we found it, the molar mass of ribose, 150 grams per mole. What is the molecular formula of ribose? Well, your first step is to find the molar mass of the empirical formula. So not the actual one, but the empirical one. So go into your periodic table, find the molar mass of CH2O. So 12.01 plus 2 times 1.01, because that's the molar mass of hydrogen, and there's 2 of them, plus 16.00. And we get 30.03 grams per mole. Now, we need to find our multiplying factor now. To find the multiplying factor, you do the molar mass of the molecular formula, the one that we found using the mass spectrometer. You divide that by the molar mass of the empirical formula, just like we're doing here. 150 grams per mole divided by 30.03. And we get 4.99, which according to our rounding rules can be rounded to 5.00. This is our multiplying factor now. Okay? What this means is that our molecular formula is 5 times more massive than our empirical formula. So in other words, if we multiply our empirical formula by 5, we will get our molecular formula. So let's do our 5, our multiplying factor, times the subscripts of the empirical formula. So each subscript, even the ones, we then get C5 H10 O5. And now we have the molecular formula for ribose. We didn't know what it was before, but when we used our mass spectrometer, we figured it out. So whenever you have the empirical formula and the molar mass of the unknown compound, you can figure out your molecular formula. Here's another sample problem for you to try. You need to figure out the molecular formula of tartaric acid based on some information provided. There's going to be a little bit of thinking you have to do here, so do try it out. So understand that these molecular formulas are important. Molecular formulas do tell you what the actual compound is. In many situations where you're, let's say, in a court case and there's a murder and we find an unknown substance at the murder scene or at the scene of the crime, it doesn't really matter where it is. We might be able to figure out the empirical formula of that unknown substance, but we won't be able to figure out but we won't be able to actually tell what that substance is unless we actually have its molecular formula. And again, many substances can have the same empirical formula. So if you look at these substances here, when you divide by 2, you'll get CH2O. 2O. So when you divide by 3, you get CH2O. Here, CH2O. Over here, CH2O. Over here, CH2O. So unless you know more information, and unless you know the empirical formula, the molecular formula, you won't be able to tell if the substance found on a suspect's shoe matches the substance found at the scene of the crime. So I do want you to read this little scenario here carefully and answer these analysis questions, as it does pertain to the importance of molecular formulas as they relate to empirical formulas. You can see we have a few more practice problems for you to do here, so molecular formula problems, as well as some problems from your textbook and from your problem set. You're now able to do problems 31 all the way through to and including 46. There are some more practice problems for you to attempt here. Please make sure that you do these problems and then take a look at the answer key after. And just to finish off, we leave you with a bit of a thinking problem. So we have the definition of a molecular formula and the definition of an empirical formula. And so I want you to think about this very carefully. Ionic compounds, do they have empirical formulas? So when you answer this question, you're going to give me, first of all, yes they do or no they don't, and then you're going to explain why that is. Think about how you find the formula for an ionic compound. Think about how you name ionic compounds. Think about how you go from the name to the formula. Think about the crisscross method and the steps involved in order to help answer your question.